Okay, so this video is about improper integration. Now, this is meant to, if you've not met integration yet, you should not be starting here. You need to be going to the A-Level Math playlist and looking at integration there, not here. This is improper integrals, it's more integration or further integration with calculus. So what you've met is proper integrals, okay? So with a proper integral, you have met, so a first year A-Level Math student would have met something like this. Okay, and you should be able to tell me how to integrate that, either via calculator or by hand, either or. So if I've got this graph, okay, y equals x squared, we know what y equals x squared looks like, it looks like something like that, and integrating between 1 and 2. Okay, but maybe a second year A-Level Math student might be able to tell me the integral of cosine of x dx, integrating between 0 and pi over 2, for example. And you should be able to easily draw the sine or cosine curve, depending whatever it's going to be, and you should be able to tell me that's pi over 2 and find that area. Okay, now what this is going to change into is what an improper integral is. So I've got the integral between 1 and infinity, okay, of 1 over x squared, something like that. Now, integrating that using A-Level Math techniques isn't so bad. As you'll see, we're going to use limits here to integrate this. 1 over x squared, that looks something like that. Okay, so trying to integrate something that looks a bit trickier, but the integral, say, of between minus 1 and 1, for example, of 1 over x squared, is nice and easy to do. However, the integral of between 0 and 1 of x log x, also I'm splitting this section into first year A-Level Math techniques and second year. So in this first section we're not going to be seeing things like integration by substitution, reversing the chain rule, integration by parts, partial fractions. We're not seeing those here. Okay, we'll see that in the later part of the video. Okay, so that would use integration by parts. So a second year student should know how to integrate both that one and that one. This is improper, and so is that, because remember, log of 0 is undefined. You can't define log of 0. However, something like the integral of minus infinity to infinity, so something like that, of 1 over x squared plus 1, okay, in respect to x, you will see that will come out to be pi, which is a very nice integral, and you will see that as we get into the video later in the course. So this is what we mean by an improper integral, something you can't actually define. So this is where we're going to be using limits in order to evaluate improper integrals. Okay, and that's what we're going to be learning about in this section. Okay, let's look at an example then. So we've got the integral between 1 and infinity of x squared in respect to x. Now we'll use limit notation. Now you've seen this in differentiation from first principles. So you write the limit. Now I'm going to write this as a limit as maybe a. We could use a, could use b, could use anything, as long as it is reasonable, okay? It must be reasonable. So we've got the limit as something is tending to infinity, that's what that means, or approaching, of the integral between 1 and a, as we know that a is tending to infinity, so that can replace that limit, okay, of x squared in respect to x. That's line number 1, the first line you make. Next line, integrating that using, remember this is first year A-Level Math techniques, so integrating that, I'm going to put that as 1/3 x cubed, integrating out of 1 to the power divided by the new power, evaluating between 1 and a. Okay, we don't need any respect to x, because we've done that. Next stage, I need to continue my limit through my integral. Okay, limit is a tends to infinity, or 1/3 a squared, summing in the a limit, and then taking away one lot, 1 cubed is 1 times a third is a third. And I've got that. So as a tends to infinity, what's going to happen? Well, that 1/3 a cubed minus a third, well, you can't have infinity take a third, so this is going to tend to infinity. Okay? So, our concluding statement, the integral between 1 and infinity, between our limits of x squared in respect to x, is therefore divergent or undifferent. Okay? That's how we can integrate this using first year error math technique. Now, it's pretty easy to integrate that, but it's not as hard as you think. You just remember, carry your limit notation through. So if we make a little side note here, carry limit notation throughout process. Okay. So if you're making notes, that's a good note to make. Make sure you're carrying little limit notation. Okay. That's how we can integrate something nice and simple like x squared using first year A-level maths techniques. Another one we'll do first year, we'll do a couple of these, and then we'll look at second year. Now, first of all, this is improper. If I draw the graph, hopefully you can see the graph in the corner here. If I draw the graph of y equals x squared, like so, I have 1, I have A, which is extended over there. So it's this region. You can see it keeps going on and on and on, so it's diverging away, okay? It's not honing in on a solution. For example, ln of 0, we know is undefined because we can't actually say what ln of 0 is. We don't know. You can have ln of 0.5, which is negative. Okay? So ln of something between 0 and 1 we know is negative, and you'll see this as we look at some examples such as ln of 0. So evaluating ln of x between 0 and infinity. We will look at that in a bit. Okay, so that is improper integrals example number 1. Okay, another example then. The integral between 1 and infinity of 1 over x squared is improper. Okay, easy way. We have the limit as a will tend to infinity. Now, that's so. The integral between 1 and a, really bad integral sign, of 1 over x squared in respect to x. Remember, this doesn't change. Evaluating that then, well, bringing the power up, making it negative, you could do that if you're confident in that. So we need to carry the limit notation through. As a tends to infinity, like so, of minus 1 over x. Evaluate between 1 and a. Now I can sub in, carry the limit notation through as the note we made on the previous example. The limit is a tends to infinity of minus 1 over a. Minus 1 divided by 1 will get you minus 1. So you're adding the 1. Okay, so it's 1 over 1 divided by that, which is equal to 1, funnily enough. So, as this is my concluding statement, as a approaches infinity, what's going to happen is this 1 over a will tend to 0. As we know from this graph that I've drawn of y equals 1 over x squared, I drew that for you earlier on, and you can see the shading region is getting closer and closer to 0, but it will not touch. Okay, this is why it's improper, so you can't actually have a physical number, okay? Because this bit will tend to 0, so as that tends to 0, we get 0 plus 1, which is 1, which is why that works. Okay? That's how we can integrate 1 over x squared between 1 and infinity using first year integration techniques. Also, note 1 over x squared, if you're wondering how I did that, that's the same as x to the minus 2. Okay? Good little note there. So using your indices laws. Again, indices laws crop up all the time. We say it needs rigorous practice because if you don't know how to do that, you can't integrate well. Okay, so adding 1 to the power divided by the new power. Okay, so you get x to the minus 1 over minus 1. Okay? That's how we get minus 1 over x, if you're wondering. Okay? Okay, that's how we can do this example. Example number 2. Okay, so in this video I'm going to be looking at another integral, and the integral is of the following. So I've got the integral like that, okay, between minus infinity and a minus 2, like so, of 1 over x cubed in respect to x. So we've got an improper integral, as we've got something we can't actually evaluate, so it's improper. So that is equal to the limit as a tends to infinity, or minus infinity should I say, something like that, of the integral between a and minus 2 of, now I can prepare the vegetables, so I'm ready to integrate, right, and there's x to the minus 3. And I'm still in respect to x, which is then equal to the limit as a tends to minus infinity of the, now I can evaluate this straight away. Now I'm assuming you know how to integrate, okay, I'm not going to insult your intelligence, but I do expect you can do a little bit of work. Evaluate between a and minus 2. Now again, keep going. Remember that note we wrote down. We wrote down a note earlier on saying that we carry the limit notation through the question. Okay, so we've got the limit is a tends to minus infinity. Now I need to sub in the values, so I'm going to get 2 lots of minus 2 cubed, which is minus 2 squared, sorry, which is minus 1 over 8. Yeah. Open up my bracket, and I need to sub in the a now, and I am taking away the a limit, which is minus 1 over 2a squared, so we've got minus a minus, so it becomes 1 over, sorry, it becomes a plus. Okay, now, as a tends to minus infinity, like so, okay, what's going to happen is, well, 1 over 2a squared, the bit that is going to minus infinity, so this bit will actually tend to 0. As this is getting closer and closer to minus infinity, this will tend to 0. Okay, so all we are saying is, as this tends to 0, that will go to 0, we've got minus an 8 plus 0, so this is going to evaluate to minus 8. And that is how we can evaluate this improper integral. Okay, now this might look like a proper integral to you. I've got the integral between 0 and 1 of 1 over x squared in respect to x. This is a hint, this is improper. Why? Because what if x was 0? Well, what if x was 0? Well, 1 over 0 squared, you can't divide by 0. So this must be improper, right, okay? So I'm going to write the limit as a tends to 0, like so. Of the integral now as a tends to 0, that limit will become a at 1 over x squared. In fact, now, let's write this x to the minus 2, just so I'm ready to integrate. As a tends to 0, and I can integrate that, which will get you to minus 1 over x, evaluated between a and 1. Well, I'm going to get the limit as a tends to 0 of subbing it in, we'll sub in the 1 first, so minus 1 over 1 will get you minus 1. Now it's become a minus times a minus, so it'll become a plus, and that would be minus 1 over a, so it'll be plus 1 over a, won't it? Like so. So as a will tend to 0, as we know, well, a tends to 0, well, 1 over a will tend to infinity. Okay? Like so. Okay? So our concluding statement would say something like, so the integral between 0 and 1 of 1x squared dx is divergent. Okay? It's not converging, it is diverging away. Because the graph of y equals 1 over x squared, as we know, is getting closer and closer, and it is diverging away from each other. Okay, so that's the graph of that function between 0 and 1. So here's 0, here's 1. Quite easily see you can't define that. Okay, and that is how we can integrate and evaluate this function. Okay, here's an interesting problem. We've got the integral between 0 and 1 of 1 over square root of x in respect to x. Now, to deal with this, I'm going to have to use the same principle as I've just used. So this is equal to the limit as a will tend to 0 of the integral of a and 1 over root x. Well, let's bring it up, make it negative. So I get x to the minus a half, don't I? In respect to x, which still needs to be integrated. We'll do that now. Now that will integrate to root x. Evaluate between a and 1. Okay? Now subbing in the limits. So we'll sub in the 1 first. Well, 2 times the square root of 1, which is 2 times 1, which is 2. And I'm going to get a minus, I don't have anything to cancel, to square root a. Okay? Now, what is that equal to? Well, as we know, as this a will tend to 0, what's going to happen is the square root of a will also tend to 0. So what we've got is this bit tending to 0. So I am ending up with just 2. So this integral is actually defined. You can define this one, which is funny because you still have to use limits in order to do it, because you can't have to take the square root of 0, can you? So you use an improper integral, but it does come out as a defined. So this is a bit of a weird one, but I thought I'd put it in here. Okay, that's how we can evaluate that integral. Okay then. The final one that I believe we're going to do using AS techniques, or first year techniques. We've got the integral between 0 and 27 of 1 over 100 over 3 square root x in respect to x, which is then equal to the limit as some a tending to 0. Well, if that's tending to 0, that'll become a. Yeah, that'll become a. Now preparing the vegetables, so I'm ready to integrate. I've got 100 x to the minus a third, yeah? You don't know where that comes from, you really need to be getting used to this, because that should be there, but you should be able to recognise that it's a cube root. Bring it up, make it negative, and obviously cube roots are written in powers. So if you've got something like x to the minus 1 over n, yeah, like that is the same as 1 over x to the positive 1 over n, which is equal to 1 over the nth root of x. Okay. So using your index laws in order to bring this up so I can ready to integrate. Still got the limit as a tends to 0. This time I'm going to actually integrate it. So integrating that, adding 1 to the power divided by the power, 50? Seems about right. And adding 1 to the power, I get 2/3. Yeah. 100 over 2/3, the same as 300 over 2, which is 150. Yeah, on go. Evaluate between a and 27. This is where I might need the calculator. But we'll see. Don't need it for that bit, so we'll see. So we need 150 times 27 to the 2/3 power. Well, I can cube root it and square it, which is 9. 9 times 150 will get me 1350. Okay, minus 150a to 2/3, because that doesn't change. So it's just some value a. Okay, what's that going to be equal to? Well, as we know, as a tends to 0, this is pretty straightforward now, as a tends to 0, then a to the 2/3 will also tend to 0. Okay, so that will approach 0 as well. Okay, so what does this mean? Well, if that's getting to 0, I just get 1350. My final integral. And that's how I can integrate this final one for using year 1 techniques with an improper integral. Okay then, more challenging example, but I'm still using first year techniques. I decided to put this one in there. Bit of fun, to be honest. Okay. Limit as a tends to 0 doesn't change at all. I've got this time the integral between 16 and a of, well, I can prepare the vegetables ready to integrate. I've got 8x to the minus half, so splitting this up into its separate fractions. And I'm going to get minus 3x to the minus a quarter. Okay, in respect to x. Okay, like so. Integrating that then, using first year techniques, still for this bit, and then we'll get into second year in a second. 16 root x, won't it? Yeah. Minus 4x, what would it be? 2 3/4? Yeah. Evaluate between a and 16. Okay. You could split the limit up here, I'm not going to, but you could do if you wanted to. We're going to get 64 minus 32 minus 16 root a minus 4a to the 3/4. Okay, so we should have that evaluated as our integral. We then got the limit as a tends to 0 of, well, what that'll evaluate to 32, is it? 32? Yeah, it is. Should be. Minus the 16 root a minus 4a to the 3/4. Okay. Okay, I'll put a bracket around that, just make it simple. Okay. Okay, so what's this going to be equal to? Well, as we know, as this a will tend to 0, what's going to happen is this bit, so this 16 root a minus 4a to the 3/4 will tend to 0, so I'm just going to end up with just 32 on its own. Alright, because the negative will form part with that. So I just end up with 32. Okay, so another more harder problem, but still using first year techniques. So year 12 techniques, if you will. Okay then, another integral for us. So we've got the integral between minus 1 and 8 of x to the minus 2/3 in respect to x. Okay, well, we can't integrate this normally. Reason why? The 0 is causing us a problem here. Because you have to understand what a limit is. The limit is between minus 1 and 8, yeah? It is not minus 1 and 8. Okay, because 0 is between minus 1 and 8. So the 0 is causing us a problem. We can't have 0 to the minus 2/3. It doesn't work. So instead, I have to split this up into 2 separate integrals, combine them together in order to evaluate this. Okay. So I've got the integral between minus 1 and 0, okay, of x to the minus 2/3. We don't need to prepare any vegetables because it's ready to integrate already. I'm going to add the other half of the integral between 0 and 8 of x to the minus 2/3. Okay, all I'm doing is splitting it up. But it does mean I'll have to write 2 limits. That's my only difference between minus 1 and a of x to the minus 2/3, plus the limit as a tends to 0, stick with a, of the integral between 8 and a of x to the minus 2/3. Okay, so I've got that. Integrating that then, still got the limit. Don't forget you carry your limit notation through no matter the integral. So I want to the power divided by the new power, well that'll be 3x to the 3rd. Alright. Yeah. Well, between minus 1 and a. of, now I need to send in the a, don't I? Well, integrate the same, innit? Between 3x to the third. This time I'm going between 8 and a. Okay? Summing in, as usual, so we've got the limit. So the limit still has to carry. Don't forget, you must carry your limits through. That's the most important thing. 3 to the third plus 3, yeah. Summing in again, I've got 6 minus be 3/8 minus the third, won't it? Or it's 3/8 the third. That'll be 3/8 just to the positive a third, won't it? Okay, which is equal to 3 plus 6. I end up with 9. Why is it 9? I hear you. So as this a will tend to 0 as the limit, this 3a to the third will also tend to 0. So that's gone, so I've got 3 plus 6, which is 9. Okay, that is how I can integrate x to the minus 2/3 with minus 1 and 8 using an improper integral. Okay, so we're going to have a look at this one. Just so you know, from this point onwards, this is second year, which is usually taught in second year of A-level maths. So we're looking at reversing the chain rule, integration by substitution, and integration by parts. Okay. So we've got the integral between 2 and infinity of 1 over x minus 1 whole to 5 in respect to x. Now, I'm still going to be using my limit notation. It doesn't change just because it's second year stuff. I've got the limit as it tends to infinity of the integral between 2 and a. Okay, so those are my limits. Of x minus 1. Now I'll bring in the power up, make it negative. I'll get minus a fifth. Minus a fifth, minus 5 instead. Still in respect to x, of course. Integrating, then. Should be nice and simple for you lot. For second year candidates. Should be getting minus a quarter of x minus 1 all to the minus 4 evaluated between a and 2. Okay, now why is it that? Well, if you know reversing the chain rule, then if you try to attempt to differentiate something of x minus 1 to the minus 4, something like that, if you try to differentiate this, what would you get? Differentiate the inside and bring it outside. Get a minus 4, because that's just 1 times minus 4, which is minus 4, of x minus 1. Bring that power down to minus 5. So we want minus a quarter of what we've got. Okay? In order to make that to work. Okay? So that's what we need. If you're wondering, that's how we do it. Okay? Good. So continuing, as I was, I've got the limit as a will tend to 0. It's 0 to infinity. Thinking of the other example I just did. Of minus a quarter. A minus 1, so I'm in the a first. It's the minus 4. Okay. I'm going to add on 2, which should get me be a quarter. Yeah. So as as this is tending to infinity, okay, what's going to happen? Well, this a minus 1 to the minus 4 will also tend to not infinity but 0. Okay. So that's tending to 0. So what am I left with? That's gone. I'm ending up with a quarter. That is my integral. So nice integral, second year stuff, using reversing the chain rule. If you're not so confident with reversing the chain rule, you can use integration by substitution. It's no different. So you just let u equal x minus 1. Okay? And integrate as you would, and you should get down to this point here. Substitute in your limits and you should get a quarter. But don't forget, you will need to change your limits as well. Okay? If you are doing a definite integral, as you will see. Right then, So we've got the integral between 3 and 84 of 7x over the 4th root of x minus 3 in respect to x. Now, I don't think I can reverse the chain rule on this, so the other option would be to use integration by substitution. So before I start, I'll let u equal the x minus 3. Okay, so what will x be? Well, x will be u plus 3, won't it? Okay, now I also need to differentiate, so du by dx. Du by dx, well, du by dx is what? Okay then, so we've got the u, got the x, got the du by dx. Now the next little bit of this question is I need to start writing this as a limit. Now what's the problem here? What makes this improper? Well, I've got this limit 3, and 3 minus 3 is 0. You can't divide by 0, so therefore this is improper. So I write it as the limit as a will tend to 3, so with some letter a of the integral between a and 84 of 7x over the 4th root of x minus 3. Okay. Next stage then, can carry on writing that as the limit as a will tend to 3, writing with all the bits that we now have found. We've got all 3 bits we can substitute back in. The integral between a and 84. Now, do you need to change the limits here? No, because we've already changed the limit with the limit of a. Okay, we've got 7 lots of x, which is the u plus 3, like so. I'm dividing that by u, which is on the bottom, while the 4th root of u is u to the quarter. Still in respect to x, of course, which is now in respect to u, rewriting that, I get du equals dx. Okay, so that'll be now du. Okay, so writing out a final line again. It's really annoying keeping a limit notation because, as you'll see, with most integrals you don't necessarily need to. So I'm going to multiply out and then expand everything on the top and the bottom. So I end up with 7u to the 3/4. Is it to the 3/4? Yeah, it would be using your index a lot of it, would be 3/4, wouldn't it? Plus be 21. Okay, be 21u to the minus 1/4. Okay, just be careful about negative there, bringing it up to the power but making it negative. Okay, and we're in respect to u. Now I can integrate, but I still need to carry that limit notation through, which is really annoying now. So adding 1 to the power divided by the new power, so I'm going to get 4u to the 7/4. So that's going to become a negative, isn't it? Or is it going to stay as positive? This stays as positive, but it's going to be 28u to the 3/4. Yeah, 3/4, wasn't it? Adding 1 to the power. I've got that. Okay. So we're breaking this down slowly. It's becoming a pain, but here we go. Got 4 lots. Well, what's u? Well, u is x minus 3, so I'm going to replace that in now. Like so. Evaluate between a and 84. We're nearly there. We are very, very nearly there. Now, this is the last stage where you have to carry a limit notation through. Limit as a will tend to 3 of, now, might need your calculator for this. So I'll just go fetch that. It'll be out the edit anyway.
Just while I'm going getting this calculator, don't forget to like and subscribe, of course. And if you are a AS level student, so only doing the first year, then please ignore this section, otherwise it will confuse you when you are doing your AS exams in the summer. So best of luck, and don't forget to like and subscribe. Back to the video.
Okay, calculator found. I just put it down there a second ago. It's 8,748. Quite big. And the other number I just wrote down of a piece of paper is 756. Okay, it's quite large. Now, minus, how can I do this then? Well, I still need to put in this a, don't I? Minus 3 to the 7 quarters. Plus 28 lots of a minus 3 to the 3 quarters. Close off that bracket. So, what's the final stage we could write? As a will tend to 3, as we know, this stage, so this, okay, will tend to 0. Well, if that's tending to 0, that's gone. So I'm just left with the 8,748 plus 756. And I should get, I got 9,504 apparently. Go to the calculator, you have to let me know. But that is how I can integrate using integration by substitution with an improper integral. Next, we'll do integration by parts. Okay, another problem now using integration by parts. We've got integral between 1 and infinity of x e to the minus x with respect to x. Now, infinity you can't actually evaluate, of course, so it becomes an improper integral. So, how can I integrate x e to the minus x? Well, I'm going to have to use integration by parts, aren't I? So, integration by parts will say that u is equal to this x. Okay, so what's du by dx? Well, that'll be 1. Okay, now what's the v here? The v will be minus e to the minus x, yeah? If dv by dx would be the e to the minus x bit. Be minus e to the minus x. Remember, e is proven very nicely in normal elements. Okay, so I've got that. Now, this is quite long, this bit, so a limit as a will tend to infinity of, now I can evaluate it immediately as minus e to the minus x, like so. Evaluate it between 1 and a, okay, and then I need to add on this other integral bit between 1 and a of e to the minus x. Now, necessarily you don't have to do integration by parts twice with this. You might be asked to in an exam, but for this case you don't. I can combine the integrals together now, so I've got minus x e to the minus x. Now I need to add on this bit, which will become adding a minus, so that'll become minus e to the minus x. Okay, just integrating using your standard results that you should know between 1 and a. Okay. Next, solving the limits of 1 and a. We'll start with the a first, shall we? So we've got minus a e to the minus a minus e to the minus a. Very complex, isn't it? And now I need to take away this other part, so just subbing in 1. We'll get minus e to the minus 1 minus e to the minus 1. Okay. I've made an error because that should have the limitation. We all make mistakes, nobody's perfect. So we've got, we can factor the negative out maybe. Yeah, we'll factor the negative out, yeah, whatever. We'll factor that negative out, shall we? We've got that. Now factoring the negative out of that, I'll get minus e to the minus 1, don't I? Yeah? Which means they will cancel, ending up with minus 2 e to the minus 1. Like so. Which is 2e to the minus 1. So we've got as a will tend to infinity. Okay. E to the minus a, yeah. that will also tend to 0, and a e to the minus a will also be 0. Because remember, the limit as some x tends to infinity of x over e to the x, like that, is that of 1 over e to the x, which is 0. Okay? And that is how we can integrate using by parts, using second year stuff. That's the video, so make sure like, subscribe, all that fun stuff. More videos come for A-level further maths, as well as for normal A-level maths. Just wanted to get these out before I crack on with it. For normal A-level maths, I've got all those to cover as well. Okay, so thanks very much, and I'll see you in the next one. Math Boy is now out of here. Goodbye, guys.